All right, let's get into it. Today, we're putting on our detective hats and diving into a really fascinating problem from a linear algebra exam. We're going to treat it like a mystery, hunting for clues hidden deep within the numbers and symbols to uncover the truth. So, here's our plan of attack for this investigation. First, we'll lay out the two puzzles at the heart of our case. Then, we're going to follow the clues for each one, step by step, to crack the solutions. And at the end, we'll talk about the really clever problem-solving strategies this whole thing shows us.
Okay, let's get right into it. Our case file today is question 4, and it presents us with two distinct, though, kind of related, mathematical mysteries to solve. Let's get them up on the board.
So on the left, we've got a puzzle about an infinite set of matrices that somehow is supposed to create a finite space. And on the right, a classic riddle about invertibility that all hinges on a very weird-looking equation. These are two totally different challenges, and they're going to require two different ways of thinking. Let's start by cracking that first case, the infinite space. So this first puzzle asks for the basis of a space that's spanned by an infinite number of matrices, a squared, a cubed, and on forever. I mean, at first glance, this seems impossible, right? How in the world do you find a finite basis for something built from an infinite list? Where do you even begin? Well, like any good detective knows, when you're faced with just overwhelming complexity, the very first step is to look for a pattern. If we can find some kind of repeating cycle, our huge, infinite problem might just collapse into something simple. So let's just calculate the first few powers of our matrix A and see what clues pop up. So we start with our matrix A. Then we multiply it by itself to get A squared. The numbers, they shift around a bit, but there's nothing super obvious yet. The real clue, the smoking gun, shows up when we take that next step, multiplying A squared by A to get A cubed. And what we find? Well, it's the key to this whole puzzle. And there it is. This brilliantly illustrates the discovery that just cracks the entire case wide open. The cube of matrix A is the identity matrix. This is the hidden pattern, the secret key we were looking for. Everything that comes after this point is just a repetition of what we've already seen. So the really crucial point here is that this repeating pattern, A cubed equals the identity matrix, it means our seemingly infinite set of powers is actually incredibly simple. It's not infinite at all. It just cycles through the same few matrices over and over and over again. Let's just look at how this works, right? Any power of A, let's call it A to the n, can be simplified. If n is a multiple of 3, then A to the n is just the identity matrix. If you've got a remainder of 1, when you divide by 3, it's just A. And if the remainder is 2, it's just A squared. That's it. Every single one of those infinite matrices is actually just one of these three. This proves that this tiny little set of three matrices, I, A, and A squared, is all we need to span the entire space W. Okay, so we've shown our set spans the space. But to be a proper basis, it also has to be efficient, and that means no redundant members. The technical term for this is, of course, linear independence. We need to prove that none of these three matrices can be built from the other two. So we set up the equation for linear independence, just like you see on screen. We combine our three matrices, we multiply them by some unknown scalars, alpha, beta, and gamma, and we set the whole thing equal to the zero matrix. Now, just by looking at the entries in that very first row, we immediately get a system of equations that tells us alpha has to be 0, negative beta has to be 0, and gamma has to be 0. The only possible solution is that all the coefficients are 0.
And that's the final piece of evidence we need. This confirms our set is linearly independent, which means it is a basis for W. And since there are three matrices in our basis, the dimension of the space is 3. Case closed on puzzle number 1.
All right, let's move on to our second mystery and see how this one unfolds. This puzzle involves a strange relationship between two matrices, A and B, and a really interesting question about their properties. So here's the riddle. We're given this pretty unusual equation connecting A and B, and we're also told that the matrix A minus B has an inverse. Our mission, then, is to use these two clues to prove that A must also have an inverse. It is not at all obvious how these pieces are supposed to fit together. This is going to require a different kind of detective work. Yeah, the solution here isn't about patiently calculating terms to find a pattern. No, instead it's about making a bold, creative leap, performing one very clever algebraic step that just cuts right to the heart of the problem. So instead of trying to isolate A directly,
The proof starts by calculating a specific product that seems to come completely out of nowhere. A plus B times A minus B. I know, it feels totally random, but as we're about to see, this is the exact tool we need to crack this riddle. Let's see where this thing leads.
Okay, so we expand the product, which gives us a squared plus ba minus ab minus b squared. Now watch this. We can group those last three terms together. Our main clue, remember, states that ba minus ab is equal to b squared minus a. The source material shows us that by cleverly substituting this relationship, that entire grouped section, the ba minus ab minus b squared part, it just elegantly simplifies to 0, leaving just a squared.
And there it is. This simple, clean equation is the result of that one clever multiplication. I know it looks like a magic trick, but it's pure logic. This is the crucial link we needed to connect our clues to our conclusion.
Now all we have to do is connect the final dots. We have a product of two matrices that equals a squared. We know one of those matrices, a minus b, is invertible. Well, that forces the product, a squared, to also be invertible. And from there, a fundamental theorem of linear algebra tells us that if a squared is invertible, then the original matrix A has to be as well. Puzzle solved. A is invertible.
So after all that detective work, what's the big takeaway here? It's not just about the solutions themselves, but it's really about the different strategies we use to find them.
In this one explainer, we saw two really powerful and completely different problem-solving techniques. For the first puzzle, the key was patience and observation, just calculating terms until a hidden pattern showed up. But for the second, it was all about a moment of insight, a single clever algebraic trick. And it just reminds us that sometimes the most complex problems don't require brute force, but instead an elegant shift in perspective. And that leaves us with a final thought. What other seemingly chaotic or infinite systems out there in the world are actually governed by a simple underlying rule that we just haven't found yet?